Okay, thank you for the introduction and for inviting to give a talk. I'm a postdoc here in the Theory Center, and today I'll be talking about a few things I've been thinking over the last 6 months or a year or something like that. So the title is a little misleading in the sense that, as probably I don't know, but the title is, Can Quantum Computing Help Us to Better Understand Quantum Fields? So there can be three answers to this. The first one can be yes, the second can be no, and then third is maybe. So I think it's safe to say that the right answer is maybe, because there are some problems in which definitely quantum computing can help us to understand quantum field theory better. But it cannot help in all the problems. If you just say that, okay, I built a quantum computer and I can solve every problem which I cannot solve on a classical computer, that's not true. That's one of the misunderstanding people have, that quantum computer is like a device or a computer which can solve everything. That's not true. And that's also true in physics or physical models, where it can only help us understand some of the problems better. And for other problems, it's probably as good as a classical computer or maybe slightly better, which does not make much of a difference anyways. Okay, so I have already explained the title, but even though I'll not get to the complete details of quantum fields, I'll try to make this set of two seminars self-explanatory, in the sense that once you understand this, you can go ahead and start reading other things, explore this world of quantum computation. So my goal is not to give you a lot of details, which probably you might not be able to follow, but give you small flavors of what you should think about and what are the way in which we think about quantum computing. So this is a very famous article, popular science article written by Scott Aronson, who is a very famous quantum computer scientist. And he has this nice picture here. So we start, the era of computing starts from this idea of abacus and things like that. And then in the around 40s, we come with the idea of Turing machines, which we now call computers. And then on the top of that, around 70s and 80s, people start thinking about this quantum computation. So you'll understand why I am denoting this by a sphere right now. We'll come back to that later on. But building on classical computers, which are built upon transistors, we do something which is based on principles of quantum mechanics. You can see a state psi here, well known from quantum mechanics. And then the eventual goal is whether it can eventually help us reach the stars or solve the most difficult problems in computation. So that is the goal. One of the important things to understand, even for classical computing or the things our computers can do, is class of problems. So there are class of problems called which belong to P, and class of problems which belong to NP. So there are two classes, P and NP. What is P and what is NP? P is any kind of a problem which can be solved by my computer or say computer in a polynomial time. What I mean by polynomial time is, if I increase the system, it doesn't increase at a rate which is faster than polynomial in, say, system size. But most of the interesting problems, and why we want to do quantum computing for physics, is because the computing time is exponential in system size. So if I take n spins, the Hilbert space goes like 2 to the n. So if the more number of spins you take, or the more number of sites you take on a lattice, on a 3D lattice, 4D lattice, whatever, the problem does not scale polynomially. It scales exponentially. And those problems, for example, there are some problems. For example, you can read about a very famous problem which goes back to Euler, where he argues that there are, say, n number of bridges in a city, and you want to take a tour of the city, and you only have to cross each of the bridge once. So can you find out an optimum way of going through all the bridges only once and covering a given part of the city? And it was shown that that problem, which is known in the literature, you can read more about it, as the 7 bridges of Königsberg, was deemed unsolvable by Euler. And in general, This problem belongs to NP because you cannot solve it in a polynomial time, because if I increase the number of bridges, take 100 bridges or 1,000 bridges, the computer cannot tell you the optimum part. But the interesting thing about this is, if I tell you what the solution is, you can check the solution in polynomial time. So for example, if I tell you that this is the way the bridges have to be crossed, then you can easily, very quickly check whether I cross each of them only once or I cross them more than once. So these are problems which cannot be solved in polynomial time on a quantum computer or on a computer, basic computer, but it can be verified in a polynomial. So these problems belongs to NP. And there is this idea of a problem belonging to NP hard and NP complete. You can read more about that if interested, but I won't go into the details. You can talk to me later if you're interested. So what happens if a problem is NP hard? So if I tell you that a problem is not solvable by a computer in a polynomial time, what do? Then the most basic thing you will say is that we have to change the definition of a computer. So we need to formally revise the definition of a computer, right? If something cannot solve a problem for me, then I have to change the thing or the setup or the machine which is going to deal with the problem. And this eventually led to the ideas that what it can be extended to. So what is the basic principle which governs the computer which we know today? It's the classical information theory or classical logic, or it's known as classical computers. It's based on the idea that everything a computer understands in terms of transistors or whatever AND gate, NOR gate, or Boolean gates inside, it is in just terms of zeros and ones. So now, when you think about nature, there are two sorts of mechanics which can govern nature. Either it can be classical mechanics, like the planetary orbits and things like that, which Newton studied, or it can be quantum mechanics. So if the classical computer is governed by classical information theory, and I want to extend the idea of a computer, the most natural thing to do is to think about a quantum computer. And that is why people started working on these things, to use the ideas of quantum mechanics or quantum information to build computers. This idea originated originally in the 1970s, but obviously it was made popular by Feynman because he was such a great teacher and he was a well-known physicist. It was made popular in the 80s by him, and then everyone started thinking about this. So this is the basic paradigm shift and how it was made popular. Okay, now what I said about NP is everything related to computer. There's an equivalent class for quantum computers, which is known as QMA. I don't want to go into the details, but it's just the quantum analog of, say, NP, which is a classical complexity class. Now, one of the things which we have to get very clear here is that in physics, we can only solve problems which are BQP, that is, which can be solved in a quantum polynomial time, but does not belong to QMA. If I tell you that, okay, here is a 4-dimensional interacting quantum field theory and it belongs to QMA, it's not easy for a quantum computer. If it is shown, if I can show that some theory is like belongs to QMA, it just means that it was NP for classical computer, it's QMA for quantum computer, so it's not possible to be solved in a polynomial time by a quantum computer. But there are some class of problems which belong to BQP, which is like I can solve it in polynomial time. And those are the quantum field theories which you can understand using quantum computers. Yes? I don't know what polynomial time is, as I mentioned. So think about a problem. So define a physical model, which is based on, say, number of sites. Take 10 sites, okay? And say, okay, and calculate what is the computer time it takes, okay? And then just square the time. Say from 10 sites, go to 100 sites. How does the time scale? Does it become double? If it is becoming double, then it's just a prefactor, it's polynomial. Or does it become 4 times? If it becomes 4 times, which obviously it does, as we know in physics from the Hilbert space, then it's not a polynomial, it's like exponential. Okay. So most of the people who want to understand it from a quantum field theory, we want to look at theories which are BQP. So for example, it was famously shown that if you want to study real-time scattering in a scalar field theory, it's a BQP problem. That means you can study it efficiently using a quantum computer. But for example, if I ask you to prepare a ground state of some spin glass, it's not in BQP, it's a QMA. Even quantum computer cannot give you exact ground state of, say, spin glass or something. So this is a distinction we have to be careful. So we want to aim for theories which belong to this class, and then we want to study it. Okay. So there's some notes I wrote, which is on archive. You can, there's not, everything almost I'll talk about is in this article. It's just, I wrote for my understanding, but it's useful for people who are getting into the field. Okay, so now let me give a brief outline of why quantum computation. I have already described this, why quantum computation and which problems can it solve. I'll give a brief definition of qubits, qudits, and Q modes. What we really mean by that. They are what, they're analogous to classical bits, which we know in classical computing. Then probably I'll also show you some very nice software demonstration which IBM has developed, known as QISKIT. And I'll show you some very small quantum mechanical problem using that software. And it's so simple that you can go home and you can play around with that software. You can just see what is happening, and you can see how things like measurement work in quantum mechanics, or for example, you can create states and do other kind of things. Then we'll go to this variational method, which is one of the most famous hybrid classical quantum algorithms, which is known today. And we'll try to see how it does for the anharmonic oscillator. So it's like a simple harmonic oscillator, but I add some cubic potential term. And then maybe we'll do go to scalar field theory. Probably we won't have time, but I'll study some, explain some other interesting models. Say, for example, this is what I'm working on right now, is like how we can understand this O3 nonlinear sigma model, which is a model which is very close to QCD. So QCD has some interesting properties, which probably you already know. It's related to asymptotic freedom in the sense that at high energies it becomes free. It has some mass gap. It has instant. So there are some smaller dimensional field theories which are similar in, which have some similar characteristics to QCD, as we know. And we want to study those theories because it's simple, first of all, and it gives us a setting where we can understand what is going on. And then I'll show you how to do the time evolution with quantum gates. The time evolution is one of the most important problems for a quantum computer. So for example, if I start with the state, I want to start, if I start with the state, which is psi naught, and I want to do a time evolution to psi t, this is one of the problems which is well suited for quantum computer, because you have to find a operator like this, right? Which will act on psi 0 to give you this. So this is one of the very famous problems known as Hamiltonian simulation problem in quantum computation, where you want to write down the time evolution of some given system in terms of this unitary operator. And note that this exponential here, e to the minus I h hat t, where h is the Hamiltonian operator. So time evolution circuits with quantum gates is one of the important applications where we want to apply this unitary operator, which is exponential of e to the minus I h hat t, where h is a Hermitian matrix, obviously. And we'll write this in terms of quantum, we have to express this as a quantum circuit in terms of quantum gates. And then probably I'll also talk about some other approaches. So there are approaches based on quantum computing using qubits. So qubit is like a two-state system. Think of spin up and spin down. So if I'm making a quantum computer, which is at its fundamental level, depending on the two-state quantum system, then it's a qubit-based quantum computation. But it can also be based on a Q modes or qudits. So qudits is a more than two Hilbert space. So spin can be not up and down, it can be at, say, it can have it can be on a circle where you have embedded with 3 points, and it can be 3, or it can be 4, or it can be infinite dimensional, for example, which is the Q modes. So if you think about a harmonic oscillator, quantum harmonic oscillator, the n in the Hamiltonian goes from 0 to infinity. So it has the harmonic oscillator is an example of infinite Hilbert space, and spin half system is a 2-dimensional Hilbert space. So those, both of them can be used to make quantum computers or quantum hardware, and that is what we'll discuss. So we'll discuss how we can use Q modes, and maybe if we have time, we'll see it using another simulator, which is called Strawberry Fields, which is for a photonic quantum computer. So photonic computer are those which are based on this idea of Q modes, because you can represent a photon by a quantum mechanical oscillator at its very fundamental level. So you can also do computing using photons. That is what people in quantum optics and other hardware, that is what they do. And then I'll briefly conclude. Okay. So before going to the idea of quantum computation, let me just tell you what is the state of the art, or what is the best we know using classical computers. So what is the best? If you give me a, say, Ising spin of Ising model, which is n spins on a line where each of them can be up or down, then the state of the art method is known as the tensor network method. You must have heard about it. So for classical computing, tensor networks is the state of the art in lower dimensional spin systems. And you can approximate this wave function, which ideally needs 2 to the n complex parameters, which is impossible for a classical computer. If you go beyond n of 20, 30, 35, you cannot do more than that. But there are smart, ingenious ways in which you can represent it using less number of parameters, that is order n. And that is what tensor networks do. So if we want to study any spin model right now, because we don't have a quantum computer, which is like functional and error corrected, we use tensor networks. So this is the state of the art for classical computing. For example, you can reproduce the interesting physics. Say, for example, if I want to study Ising model, which has exactly known solution from the work by Onsager in 1944, for which he won a Nobel Prize. If you want to study this system, you can do it in less than a minute of computer time, and you can reproduce the exact energy. So tensor networks are very powerful, and classical method, these are kind of an alternative to Monte Carlo in some sense, but for lower dimension, it's much better than other conventional methods. But with tensor networks, the scalability is a problem. We can do lower dimensions, but as soon as we go to higher dimensions, say, for example, 4-dimensional Ising is much harder for a tensor network. So scalability is a problem, and that's coming just because you have more degrees of freedom. 1 dimension, everything is easy. 2, it's become a little harder, and eventually in 4 dimensions, it's like much harder. So tensor networks cannot help you all the way. So this goes back to the famous quote by Feynman, who said that nature is quantum mechanical at its very fundamental level. We cannot simulate it classically in an efficient manner, even though we have efficient algorithms. So even though you have very smart algorithms like DMRG, MPS, tensor networks, people have come up with this over the last 20 years, very interesting algorithms, but you always hit some sort of a roadblock. You can never simulate this. There's always a problem. And that's just because it's quantum mechanical. If you want to describe it using classical computer, you'll eventually hit a roadblock. Okay, so Feynman wrote this article back in around 84, 85, which made it very popular among computer scientists and also physicists. The title was Quantum Mechanical Computers. He talked about computation with a reversible machine. You want a reversible machine in as for a quantum computer, because laws of quantum mechanics are reversible. You have this unitary evolution. There's no loss of probability. What is the general thing people say? And everything is reversible. So we want to do the article discussed about different sort of gates which have to be introduced to do quantum computation on a reversible machine. So this is a very interesting article. I think after what I discussed in set of 2 lectures, you can go back to this article and read it very clearly. We'll be talking about a lot of things which he already mentions in the article. for example, controlled NOT. I'll show you what a controlled NOT gate is, what are other sort of gates. So that will give you a basic foundation to study this. Okay, so what are the two approaches I mentioned? Let me just recapitulate. Yeah. The first one is the discrete variable quantum computing, which uses qubits to perform computations. And there are three steps in general. First is I want to write down what size 0 is. Right? I want to write down what size 0 is. The second is implementing this exponential of e to the I h hat t. And the third step is once I do this, I do measurements, which have to be done by some external observer. And it's the usual sense in which measurements are made in quantum mechanics. So for continuous variable also, which is like an example of a harmonic oscillator, we have the same sort of steps. Prepare psi naught, prepare unitary time evolution, and then measure it. So these are the different approaches, but the basic idea is the same. So one of the fundamental things which we learn when we do classical logic gates or classical information theory is that you represent the information in terms of a 0 and a 1. And then you add some sort of a gate, which can be an AND gate, OR gate, and some other sort of gate. And then you see what the output is. In terms of quantum mechanical computer, we always talk about states. So for example, if D is equal to 2, which is the qubit, we represent it by a ket 0 and ket 1. So is there anyone who is not familiar with this notation? Okay, so that's good. Okay, so this is D equal to 2. I just 0 spin up, spin down. If it is D greater than 2, I can write, say, for example, a given state in terms of not just 0, 1, but in terms of 0, 1, and 2 with some coefficient, which is alpha, beta, and gamma. And obviously to normalize the states, we know what alpha square, beta square, gamma square should be. They should be equal to 1 and things like that. But with Q modes, we have D equal to infinity. So instead of D equal to 3, which is the case here, you can have like superposition of infinite number of states. Now you saw in the article which I showed in the first few slides of about the sphere. So this sphere is known as Bloch sphere. It's like an imaginary sphere, which is nice to visualize things in quantum mechanics. So for example, the 0 is like a north pole of the sphere. 1 is like a south pole. So think about this as spin up, spin down. And then you can have other states which are written like alpha hat, which are written as psi. There's some angle theta. This is x, which is plus. So for example, plus state is just given by, in this figure, the plus state is just given by uniform superposition of 0 and 1. And similarly, negative is just, which is on the other end of that, is given by this. Right? So that's what plus and minus is. For example, this is plus, the other side will be minus, the negative x direction or the axis. And that is how you represent a given state. This is the qubit representation on a Bloch sphere. So we can represent any state like this. So, okay, now we understand what the states are. We'll be mostly talking about qubits. So the state is 0 and 1. That's all they are, 0 and 1. But they are a state, quantum mechanical state. They are a vector. It's not like classical where it's not. So these are vectors in a given vector space, which is the Hilbert space. So this is 0 or 1. Now, once we have this 0 and 1, what do? We have to manipulate them. We have to manipulate them in the sense that we take 0 and 1, pass it through something, and then see what we get. Okay, so that's where the gates come in. And those are called quantum gates. And they are unitary, as they should be, because if I'm transforming some given quantum state to some other quantum state, the transformation has to be unitary. So the most important gate is the gate which is represented by H, which is the Hadamard gate. So Hadamard gate is given by this matrix, which is written here. What does it do? If I take a 0 state, pass it through a Hadamard gate, it gives me a plus. So these gates here, which is the H gate, you see that there is just one wire going through. And the fact that it has just one wire means that it's a 1-qubit gate. For example, I can also have 2-qubit gates, as we'll see in the next couple of slides. Those are 2-qubit gates. There can be 3-qubit gates and things like that. So this is 1-qubit gate. It's only going to manipulate 1 qubit. There can be 100 qubits, but this will only act on one of them. And this acts like this. Now we have 3 famous matrices, which we know from quantum mechanics, the Pauli matrices. They have a corresponding gates, X, Y, and Z. I'm not so Y is represented here, X is here, Z is here. What does X do? This is just the Pauli matrix we know. What does X do? X takes a 0 and flips it. So it takes a 0, spin up, goes spin down. What does a Z gate do? It takes a spin down and then this puts a negative sign in the front. So it just transforms 1 to -1. And similarly, different gates will act differently. And this is a set of gates which are frequently used, and they are all 1-qubit gates. So this is H, X, Z, Y. This is a phase gate. This is a rotation gate, rotates by angle theta. This is again a phase gate, but with some fixed value of phi. And this is a T gate. So these are different sort of gates which you see in any quantum circuit you probably come across in textbooks or articles online. But there are other gates, and that's what we call the controlled control knot, which you also saw in article here by Feynman, controlled knot. There's a controlled knot and there's a controlled knot. So let's look at first what controlled knot is. And that is how we write it. C means for controlled, and then knot is just the knot gate. It's also known as CX gate. So before understanding this gate, let's go back and do a quick recap of the classical Boolean algebra. If the inputs is 0, 0, 0, 1, 1, 0, 1, 1, then the AND gate will only give you a high when both the inputs are high. OR gate will give you a low only when both the inputs are low. And exclusive or XOR gate gives you a high when even number of things are high. For example, if there is 0, 0 or 1, 1, it gives you 0, but the clause is 1, 1. So this is the classical algebra. Similarly, in this case, you see that suppose I have two, now I'm saying that the C0 is a 2-qubit gate, and that is why there are 2 wires here. So what are the 2 input states? They can be A and B. So 0, 0, 0, 1, 1, 0, 1, 1. What happens to 0, 0? It just goes to 0, 0. 0, 1 goes to 0, 1, 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. Now, the way to understand this is quantum mechanics needs, let me finish and then you ask. I'm pretty sure I'll answer what you want to ask. So there are 2 inputs and there are 2 outputs. Why do we have 2 inputs and 1 output in classical case, but 2 inputs and 2 outputs in quantum case? Because we want to be reversible. Given an output, we always want to reproduce what the input was. That's not possible always in classical computation. Because, for example, if I tell you that OR gate is giving me 1, you can never tell me what the input was. But in this case, the output and input both have 2 bits, and it is always reproducible. So it's like it has to implement unitary transformation. So that's fine. Now, what does it do? The output, which is stored in this register, will be flipped if the control line is high. So for example, if the control is 1, this B is flipped. So for first 2 rows, this is not flipped. So I get 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. But in this case, 1, 0 goes to 1, 1. Because A is high or 1, so B gets flipped. In this case, A is high, so B gets flipped and I get 0. And that is what C0 gate does. C0 gate looks at the control line, and if the control line is high, it flips the input bit. And this is one of the most important gates which people use in quantum computation. Okay, so there are other representation of this gate in terms of outer product, which you must be familiar with. So you can write this gate, which I mentioned here. You can write the matrix representation of this gate in terms of outer product. So for example, this is a ket vector, Ra vector, Kronecker product with an identity matrix. And this gives you So this gives you a matrix which is a 4x4 matrix, and that is the exact representation. One thing I want to add is these are all 1 qubit gates, so these are all 2x2 matrices. The C0 is a 2 qubit. There are 2 wires or 2 qubit gates, so C0 is a 4x4 matrix. If you want to write down the matrix representation of C0, it's a 4x4 matrix. So keep that in mind. If I take a 3 qubit gate, it will be an 8x8 matrix. Okay, so again, we go back to this poly X, poly Y, summarize the gates, Hadamard, phase, pi by 8, control knot, which we already saw. The notation is this. This is a notation you will frequently come across. There's a solid blob on the top, which refers to the control line. And then there is this cross, which is like, if the control line is high, flip this input. That's what this means. This is the matrix representation for control knot. This is the matrix representation for control Z, similar to control X. This is a swap gate, which is also used in textbooks. Swap gate is just basically, if you have a state like 0, 1, it will swap the qubits. It will make it 1, 0. And then there is another gate, which is one of the important gates in quantum computation because it is related to the universal nature of quantum computation. It's called the controlled control knot gate. So double controlled knot. So it's exactly like this, but instead of 1 control, now I have 2 controls. So how do I draw this gate, which is the controlled control knot? It's simple. It's a 3 qubit gate. So I draw 3 wires. First of all, there are 2 control. So I draw 2 of these as solid blobs, and then the third one is like this. And then I connect them. And this is CC naught. And this is also known as Toffoli gate. So this is a 3 qubit, 8x8 matrix, doubly controlled gate, which acts similar. So if I ask you to write down the logic table for that, you can probably easily guess. It will only be flipped. If A and B are high, the C will be flipped. It's just similar to what we saw in this case. So, and the matrix representation is given by this matrix. So if you have a state, you act out, you pass it through this gate, you can find out what the output state is just by using this matrix representation. Okay, so 2 special features of quantum mechanics, which we have right now. And I am emphasizing this because first of this, we have already seen. Superposition, why do I say we have already seen? Think about the Hadamard gate. What is the Hadamard gate doing? Hadamard gate is taking a 0 qubit and giving a plus state. And plus state is a uniform superposition. It's uniform because both the things have probability of 1/2. It's a uniform superposition state. So this is already implementing one of the very important features of quantum mechanics, which is the superposition. And we'll see later on what happens to the entanglement. How can we generate entanglement using these gates and input and things like that? So 2 special features of quantum mechanics. One is the superposition, that unlike the classical bit, it's not just 0 and 1. It can be in a superposition state. And as you increase the number of bits, the number of possible superposition number of states increases. It can be like what I showed was a uniform superposition, but it can be a non-uniform superposition and things like that. And the second thing is the entanglement. How are, for example, I'll show you an example for 2 and 3 qubits. What do I mean by entanglement? And how can we represent them using these gates, which I showed you? For example, we'll see that it is, if we want to generate a 2 qubit entangled state, which is also known as a Bell state, you will need to use one of these gates. For example, C0 gate. We'll have to use C0 gate to generate a 2 qubit entangled state. And we'll see that. So these are 2 basic special features of quantum mechanics, and we can directly see that how it arises in terms of computing or in terms of gates. So what I'll do now in the remaining time is, if you have a laptop, you can follow me. If you don't have a laptop, you can just watch on the screen. I'll do a couple of things and I'll show you some of the things we have played around with, and I'll show you how those things work. So I'll be using this QISKIT, which is developed by IBM, which is like a simulator. Simulator is something like not a real quantum hardware, but like a proxy in the sense that, like, I like to think about it how airline pilots do a simulator rather than like on a real plane when a new plane comes, for example. So it's like a simulator, you can have experience. Then once you understand this, you can put to the real quantum hardware, which are accessible. You can make an account, IBM Q and things like that. And you get different sort of qubits, and you can do those experiments directly on that. But the good thing about this is you can do it directly on your laptop. You don't need to install anything. You just need to open Google Collaboratory. I don't know whether you know about that. Just open a Google Colab notebook, just pip install something, and then you're good to go and ready to play around with these gates and states, which I discussed. A lot of working codes are given in the article which I mentioned. Okay, so this is the basic idea. If you have a Google Collaboratory, if you have a Google account and you have used Google Collaboratory, I suggest you open Google Colab and type the first line. It will install the quantum computing, this QISKIT for you. And let's see. So if you have opened the Google Colab, you can just put in the first line, which is pip install QISKIT with the following end line. We'll do this in this at the starting of the second lecture. So let's not get stuck here. I'll just explain briefly what this means. I'll show you a demonstration. You can do it. The code is there. The more important thing is to understand what the code is doing. So the first thing is to install this QISKIT software, and then we install all the necessary libraries from the QISKIT. And then what we want to emphasize is how many qubits do we want to use. So we want to use a 3 qubit. We want to construct a 3 qubit state, and that is why we specify that the Qn, the number of qubits, is 3. Now, once we have specified the number of qubits, which is 3, what do I do? The first thing I have to do is I have to make a circuit, and then I have to tell it what are the gates we want to apply. So circ is just a circuit, constructs a 3 qubit state. So I'll go step by step on the board so that you understand what I'm talking about here. So the first step, the Qn equal to 3 quantum circuit 3 gives you a circuit like this. Just 3 wires. Then I tell it to do H on 0. H is nothing but the Hadamard gate. For example, it does a Hadamard gate on the first qubit. So for example, like this. Then I tell it to do CX, which is the control NOT gate. Now remember, Hadamard gate was a 1 qubit gate, but control NOT was a 2 qubit gate. So 0 qubit is the control, and then we have a 1. So what does it do? It does a control here, and then it does a 1 on this. And there's nothing happening yet to the third wire. What is the third step? Now I do a control NOT gate, but between 0 and second qubit. So this was 0 and 1, but now I do between 0 and third. Nothing to the second one, so it just passes as it is, passes as it is, passes as it is. This is the input state. This is the output state. So now, once we have done this, one thing to note is that when I'm initializing, everything is in 0, 0, 0. So psi 0, or the psi input, is a 3 qubit state represented by 0, 0, 0 get vector. And then I do this, and then I get some output vector, which I can measure using this command. So I want to get out the state vector from this instructions I've given using this circuit, and I want to display what the state vector is. Now, before displaying what this is, you should just think about what it will be. What do you think the output state should be in this case? We can find that out because we know how these how these gates act. They cannot move. Yeah, okay, no, it's fine. Thank you. Yeah, of course. So I already told you that this H acts like this, right? And the C naught acts like something like this, is a matrix represented by this. So we can find out what this output state will look like just by doing that. So let's start with that. So 0, 0, 0. What happens to this one? So there are different ways you can do this. You can start by saying that this is Q0, Q1, Q2, or you can use also Q0, Q1, Q2, but I'll start with the what people call a little endian notation, which is like the rightmost bit is Q0. So this goes to so this was the state here. What is the state at this point? Psi 1. This is psi 1. What is psi 2? I'll leave that to you to work it out. What is psi 3 after this? What you'll see is at the end, psi 3 is nothing but and it's a very famous 3-qubit entangled state, also known as GHZ state. And one of the authors got a Nobel Prize recently for his work. Yes. So it was a very famous state which was constructed, which is an entangled state of 3 qubits. And that is exactly what this is. 0, 0, 0 plus 1, 1, 1 divided by square root of 2. And how do we construct this using QISKIT? You can see it here. At the starting of the second lecture, hopefully with the computer problems behind us, I'll show you that this returns exactly this. So, but how will it display this? It will display a column vector of 8 elements, where the first element and the second element will have a coefficient of 0.70 something, which is 1 more square root, and everything else will be 0. And that you should also have obtained if you did it using Google Colab. So anyone reached this point and got this? Okay, very good. So those who have done it know what I'm talking about. Those who have not will see at the starting of the second lecture. So this is how we can implement, for example, very simply implement a 3-qubit entangled state. And we'll see more about how we can implement a Bell state and do other sort of measurements later on. Okay, so for example, if you have done this, then you can construct any given number of quantum bits or classical bits using a technique like this. In this case, we had just constructed a quantum circuit which had qubits. But in this simulator, you can also construct a quantum bits and a classical bit. So for example, if you write quantum circuit 4,2, it just gives you 4 quantum bits, which is qubits, and 2 classical bits. And this is what is represented by QC. Why do we need to have classical bits? We need to have classical bits sometimes because at the end of some computations, we want to measure it. So for example, often you will see that, okay, these are the 3 qubits, and then there's one classical bit which is going below this. And that's what people measure. So there's a sign of measurement like this. So for example, if I want to measure what is happening on this qubit or measure all of them, you need to have some sort of classical register. So those are meant for measurements, and that is why we include them. And we'll see why they are useful when we work this out. Now, this example was a little more complicated because it was 3-qubit entangled state. But now we go to something a little simpler. We just add initialize 4 qubits and 2 classical bits, and then add a Hadamard gate to the first qubit and do a control X to the 0 and first qubit, where control line is the first entry, which is 0. Now, can anyone guess what is the output state we'll eventually get here? Okay, so the output state you'll get here is what we call a Bell state. You'll get a Bell state here because it's very simple to see. You have 2, 0, 0. You do a Hadamard on the 0, and that changes it to and then you do a control X on 0 and 1. So that changes it to something like this. And this is what we'll see later on. So what can we do? We can measure these states. So for example, we can measure the 0th first qubit with the first classical bit. We can measure the first quantum bit with the first classical bit, because we have now a circuit which is consisting of 2, 2. And you can also draw this circuit. So if you have Google Colab open, you can write this and you can draw qc.draw with an open parenthesis. And you will see that this gives you a circuit like, for example, what we were drawing here. For example, if you can also do a QCS, we are already doing that. So you can also do a circuit.draw and it will give you a circuit like this. So that is what will happen with QISKIT. And one of the things which is nice about QISKIT is you can visualize these states on a block sphere. So as I mentioned before, several slides ago, is that you can always visualize where it lies on a block sphere. So for example, I create a random state, just create a random 2 qubit state, which is, this is 1 qubit, this is another qubit. And you can visualize it where it lies on a block sphere. So if I initialize a random state like 0, 0, both of the arrows or these arrows will be pointing up. If I initialize 1, 1, both of them will be pointing down. So it gives a very nice visualization of where the 2 qubit states are. So you can also use this. So I think for this, I think that's all. We want to go back and implement this. So we'll do that at the starting of the next lecture. So yeah, for the first lecture, we'll, I guess, stop here and then carry on from here. Okay. You don't need, that's a good catch. So he's asking about why we needed 4 quantum bits there. We did not need 4 quantum bits. It was just written to get your attention, actually. So we don't need 4 because we are not doing anything with the second. So we are just using 0, 1. So that's why it was just changed to 2, 2 here. So yeah, that's good. But you don't want to initialize more qubits than you actually need, but you can do that. Just like you can write 10 here, if it is allowed. Okay, thank you.